This video, we're going to revisit section 16.7. We were talking about acid-base properties of salts. And then we are going to work through this learning check. So I started it in one section, but didn't really even touch it in the other. So let's do it here. It says, determine the pH of a 1.0 molar solution of sodium acetate, and then we're given Ka for acetic acid. So sodium acetate, we should first figure out what we're working with. This is a salt. We have a counter ion sodium. So let's see, where will I have more space? We'll go above. So this sodium acetate will dissociate into Na plus and then acetate. Na plus sodium ion is the spectator ion. It is the counter ion for strong base sodium hydroxide, so that doesn't have acid or base properties. But C2H3O2 minus, this is the conjugate base of acetic acid. It's negatively charged, it's going to be basic. So we have a basic solution. And then we're given some information about acetic acid. Now I know you don't have the formula for acetic acid. I will give that to you here. It is acetate from sodium acetate, but with a hydrogen. This is a acid. It's called acetic acid, but it's a weak acid. So if we add it to water, it will donate a proton to water, which will become H3O plus. And then as it loses the proton, it becomes C2H3O2 minus acetate. So sodium acetate has the conjugate base of acetic acid. It's acetate. Okay, so that's really just understanding what sodium acetate is. But acetic acid is not what's added to solution. It is sodium acetate. Sodium acetate is basic. So when that's added to solution, we have the base reacting with water. Because it's basic, so let's write here, this is base. We said it is basic. Water is going to be the acid. So it will form a acetic acid and hydroxide. So the base accepted the proton. This is now the conjugate acid. And then this will be the conjugate base. The acid donated the proton and became OH minus. So I just want to reiterate, maybe clarify, organize what we've done so far. In the actual solution, it says the solution is made by adding sodium acetate. So that is this guy here. We know sodium acetate will dissociate into Na plus and C2H3O2 minus. Na plus is a spectator ion, so it's not really needed in the actual reaction, but it could be added as both a reactant and a product. It's a spectator, so it doesn't do anything in the reaction. It's not involved in this acid-base reaction. Okay, so spectator ion, not involved, could be added to the reaction. But the acetate is what is added to the solution. This is what will react with water. We determine that it is basic. We can suspect it because of the negative charge. but also it is the conjugate base of acetic acid. And yes, I gave you this formula so we could determine it was the conjugate base. Okay, so because this is what's added to solution, when we're actually going to think about this solution and find the pH, we need to think about how this base, which has basic properties, interacts with water. It's basic, so water will be the acid. Now we're just thinking about a classic acid-base proton transfer reaction. The acid donates a proton to the base accepts a proton from the acid, and this is how we get our products. Now that we have the equilibrium reaction written out, we need to determine the equilibrium concentrations of hydroxide so we could find the pH of the solution. Remember, pH will eventually look for negative log of H3O plus, or we could do 14 minus POH to calculate the pH. This is a weak base that's getting added to solution, so we have to find equilibrium concentrations. We'll do our ice table. I'm going to leave the spectator ion off of the ice table, and I'm going to leave water off of the ice table. So I give some more room there. Okay, so we were told it was a 1 molar sodium acetate. So we have 1 molar acetate, initially 0 products. So 0 acetic acid and 0 hydroxide. To reach an equilibrium, we have to use up reactant and produce product. So we have minus X for reactant plus X for products. Then we have to think about what other information we have. We don't have any equilibrium concentrations, but we have Ka for acetic acid. Ka for acetic acid almost gives us something. Well, it does give us something helpful. It's just not as direct as what we've seen before. This is where we actually need a new relationship. We haven't covered this yet or used this yet. But if you have Ka for a reaction, Kb for a reaction, multiply them together, you get Kw. Why is this important? Well, we have not added acetic acid to solution. We've added the conjugate base of acetic acid. So when we calculate the equilibrium ratio of products to reactants, this is actually Kb. So Kb for acetate, for sodium acetate, is concentration of this conjugate acid times concentration of OH minus divided by acetate concentration. All right, so that's Kb because we're adding base. We're given Ka. We can find Kb, the value of Kb, by using this relationship. So let's do that. Let's find Kb. Kb is equal to Kw divided by Ka. Kw is this known value, also on the periodic table sheet, 1 times 10 to the negative 14. Ka is provided, 1.8 times 10 to the negative 5th. So Kb is equal to 5.6 times 10 to the negative 10. And just a reminder, we need Kb instead of Ka because sodium acetate, what is actually added to solution, is a base, not an acid. All right, we have the Kb value. We can set up an equilibrium constant expression. We're going to have to set it up in terms of x. So we have for acetate 1.0 minus x. For acetic acid, equilibrium concentration is x, and same with hydroxide. So this is x times x divided by 1.0 minus x. And this is equal to let's actually do this approximation first before we set it equal to Kb. This is a weak base situation, so we can simplify this to x squared over 1.0 because, again, x is going to be very small. We did this a few slides back. X is small, so if you subtract a really small number from 1, it's approximately 1, so we can simplify there. All right, let's say this is equal to 5.6 times 10 to the negative 10. Multiply both sides by 1, get the same number here. So let's take the square root of both sides to find the value of x. X is 2.4 times 10 to the negative 5th. Now, we can never forget where we're going, right? We're trying to determine the pH of the solution. Finding X gives us the equilibrium concentration of OH minus. So we can say, let's write this here. Concentration of OH minus at equilibrium is 2.4 times 10 to the negative 5th. This is where we need, so when we need to find pH, but we have the concentration of a base, this is where we can invoke one of the two methods. Method 1 was finding pOH and then using that to calculate pH. Method 2 is calculating H3O plus concentration by using Kw and then calculating pH. I've been using method 1, so I'm going to continue with that. We'll calculate pOH first, which is negative log of this concentration. And this is 4.63. I'm just going to draw a line here to help guide where we're looking. So pH is 14 minus pOH. So 14 minus 4.63. This is 9.37. So that is the final answer, the pH of a 1 molar solution of sodium acetate. So there's a lot of different concepts that are needed for this question. We had to first use what we knew about the properties, the acidic or basic properties of salts to determine that it's basic. We wrote out the equilibrium expression, Ice table used Ka and Kw to find Kb. Approximation of equilibrium concentration, find X, find OH minus concentration, POH, and then finally pH. This is a monster of a question. There is one more slide that we really didn't finish in lecture for this chapter, so I'm going to scroll down to that. It's a completely different concept now, so if you need to pause, just pause the video before we go there. But it is right at the end, actually I think the very last slide. Yes. So we had talked about Lewis acids and bases. Lewis acids have open shell atoms, bases have electrons that they can share. Bases donate electrons, acids accept electrons. So we looked at these three reactions. We talked about the first one in lecture. We are identifying the Lewis acid and the Lewis base in the following reactions. For the first reaction, if you drew out the structure of H2O, you would see that there are no open shell atoms or any atoms that can accept additional electrons, and there are non-bonding electrons, so that's a good indication that it's a base. The acid, the other reactant here, aluminum 3+, well, if you have a metal cation, that can be a Lewis acid. It can accept more electrons. All right, so we kind of did that one in class. Let's look at reaction B. An O2-, so we can pretty easily draw that Lewis structure. Oxygen, neutral, has 6 electrons. O2- will have 8 total. So this reagent has a full octet, and it has non-bonding electrons that it could share. That's a pretty good indication this is the base. But let's look at the other reactant as well. Even without drawing the Lewis structure, although we could, but let's not. Let's just think about this reagent here. So sulfur, let's remember that sulfur, it's in row 3, so we can call it hypervalent. Valent, think of valence shell. It can hold more than 8 valence electrons. So third, fourth, fifth period. So it is in the third period, but if you have an atom that's in the third or the fourth or the fifth or the sixth and so on, it can hold more than 8 valence electrons. The octet rule is a good rule for row 2. It's a good first assumption for row 3, but you have to keep in mind that row 3 and higher, like 4th, 5th, 6th, can hold more than 8 valence electrons. We know for sure that oxygen, O2- here, oh, I didn't mean to do that. O2- cannot accept any more electrons. It has 8 and it's in row 2. It can't have more than 8. So the other reagent here must be the Lewis acid that can accept electrons. Lastly, we have H+ and H2O. We drew the H2O Lewis structure already. I'll draw it again right here. All atoms are closed shell. They cannot accept any more because hydrogen can only have 2 total, oxygen can only have 8, and those are already satisfied. So this is likely the base. And then H+, if you remember what H+ is, it's hydrogen without any electrons, so it can accept electrons. This is the acid. All right, open shell atoms or atoms that can accept electrons can act as a Lewis acid. Molecules or atoms with electrons can share them and be the base.